Day 11, density. Density is mass over volume. Now, when you think of density, you might be more familiar with the question, why does ice float on water? Well, ice floats on water because it's less dense than water. Or what if you throw a rock into water? Why does the rock sink? Well, the rock sinks because the rock is more dense than water. Density is mass over volume, and so we can just go ahead and write that as D is equal to M over V. Now we can switch some things around, like we can multiply both sides by V, and we could say M is equal to density times the volume. In other words, we can solve for the mass. Or we could solve for the volume and switch that around, multiply both sides by the volume, and divide both sides by density. And we would get the volume as the mass divided by density. So we can rearrange these, but we need to have at least two of these three variables in order to solve. Let's do a problem. A metal ring has a mass of 96.5 grams and a volume of 5 cubic centimeters. Determine the density of the ring and the identity of the metal. So density is mass over volume. We write down our equation. Density is mass divided by volume. Now we plug in what we know. We have 96.5 grams, and it's 5 cubic centimeters. And so we write down our equation, we plug in what we know, and we solve. This is our strategy for success. Write down our equation, plug in what we know, solve. And now we have density is mass over volume. We plug in our calculator, 96.5 divided by 5, and we get 19.3 with units of grams per cubic centimeter. Okay, well, how are we going to determine the identity of this metal? Well, it turns out if we go to a density data table, so that's just right here. I have it all set for us with a whole bunch of different substances and their density listed. And so if you go down and you'll find, 19.3. That's the density of this stuff called Au. Now Au is gold. The ring is made of gold. You might not know that Au was gold, and that's okay, because this week we're going to be studying the periodic table and we'll get to learn all the different elements and their symbols. So don't let that bother you if you didn't know that Au was gold. Let's look at some more stuff. Suppose we go through and we say density is equal to mass over volume. Now, if I increase the mass, what do I have to do to the volume so that the density remains constant? I would have to increase that volume so that the density remains constant. This is what we call a direct relationship. Think of it like this. If I said the number 10 is equal to x over y, and I set a data table, an x and y data table, if I put in 10 for x, y has to be 1. If I put in 20 for x, y has to be 2. If I put in 30 for x, y is 3. As x increases, 10, 20, 30, what does y do? It increases as well, 1, 2, 3. So they increase in the same direction. This is called a direct relationship. We also see this with the formula of volume is equal to mass over density. And so if the volume is to remain the same, now if I increase the mass, I increase the density. Or a different way to look at things is if we solve for the mass. Mass is equal to density times the volume. Now this is a little different, because if the mass remains constant, if the density increases, the volume has to decrease. Or if I let the density decrease, then the volume has to increase. This is called an inverse relationship. So we have a direct proportion, or we have an inverse proportion, or indirect relationship. So we have these two things that we need to look for. Here's a good example with this mass is density times volume. Let's just use 10 is equal to xy. If I did this and set up my data table, then if I let x equal 10, y is equal to 1. If I let x equal 20, then y has to be 1/2. If I let x equal 30, then y has to be 1/3. Notice as x gets bigger, y gets smaller. Likewise, if I went and said x and y, if I let x equals 10 and y equals, say, 1, what if I let x be 5? If x is 5, then y is 2. If x is 1, then y is 10. So as x decreases, y increases. So this is called an inverse or indirect proportion. So tell me, what happens if I say, if I go over here and I say if I doubled the density, what does the volume have to be for the mass to be constant? You say, I have to get this formula, m is equal to density times volume. So if I want the mass to be constant and I double the density, what will the volume have to do in order for me to get back my equation? Mass is density times volume. I would have to have half of the volume. The volume would have to go down by 2 so that those 2's would cancel and I'd still get mass is density times volume. So if I double the density, I have to have 1/2 of the volume. Well, what if I tripled the density? What if I triple the density? How does the volume affected? That's exactly right. I'd have to have 1/3 of the volume. I'm sure hoping that you said that. So the 3 and 3 would drop out, and then we would be able to get mass is density times volume again. So you double the density, you have the volume. Triple the density, 1/3 of the volume. 4 or 5, if you had 5 times the density, it'd be 1/5 of the volume. But what if we have something like this where it's a direct relationship? Volume is mass divided by density. So if I have 5 times the mass and I want to leave the volume constant, what does the density have to do? I have to have it by 5-fold so that those 2 5's would cancel. Mass divided by density. So if I have 5 times as much mass, I have to have 5 times the density in order for the volume to remain constant. That's what we need. So if I doubled the mass, I'd have to double the density. Triple the mass, triple the density. Likewise, over here in this first step, density is mass divided by volume. If I have D equals m over V, and if I want to leave the density constant, if I triple the mass, what do I have to do to the volume so that the volume, so that the density remains constant? I'd have to triple the volume. I have to triple the volume so I get back my original ratio. So I'm hoping that you saw that to be useful. One of the things that's also useful is going back to the concept of a slope. And let's use this. Mass is density times volume. Now, I'm going to write it again, but I'm going to use mass is equal to density. I'm going to write it out in words. And I'm going to do this for a specific reason. And that is because I want to think about placing this in a graph. What I'm trying to say is, what if I were to make a graph and I were to have volume on this axis and I were to place, say, mass on this axis? Let's just have mass with units of grams, volume in units of cubic centimeters. And so if I were to have some sort of data, maybe I did some type of experiment and I had some data. And so then what I did was I want to draw what's called that best line fit. Draw that best line fit. Go through some of those data points. Try to get the best line, the best linear line that would fit through there. And then I would pick a couple points. and I'll call this point 1, which is x1 and y1. And then I would pick this point, which I'll call point 2, and that'll be some position x2 and y2. Now, if I calculate the slope of this line, well, that's just the rise over the run. So the slope of the line is usually written as m, which is that rise over run. And so what is the rise? Well, that would be y2 minus y1. What is the run? x2 minus x1. This is how we calculate the slope. And the slope is usually given this symbol m. So this is kind of neat. Mass divided by volume, the slope. But you know, this is what we would see like in a math classroom. But how do we relate that to a science classroom? Well, what we do is we say, hey, what's that equation of a straight line that we just did? That equation of a straight line is y is equal to mx plus b. B is that y-intercept. Notice that there's nothing here. There's no constant term here. And on the y-axis, notice, so I put that b equal to 0. But the y-axis, I put the mass. And on the x-axis, I put the volume. So guess what the slope represents? Absolutely. It has some meaning. It represents the density of the object. So the density can be related to the slope if we graphed it. And so y is equal to mx plus b. Now I have one more, maybe two more things really quickly to show you. Now density is equal to mass divided by volume. Well, what if we wanted to find the density of some spherical object? In this case, I'd have to use that volume of a sphere, which is 4/3 pi r cubed. Or what if I had the density is equal to mass over volume and I had some rectangular shaped object? You know, what if I had an object that looked like this and I wanted to calculate the density of this object? Well, remember, I'd have to use the volume of a rectangular surface, which is that length times width times height. So I might have more calculations to do or more variables to look for rather than just mass, volume, and density. I might have to look a little closer to the volume. Or I could, instead of giving a value expressed in mass, remember our mass to weight conversion? If I wanted to go from mass to weight, how that works? Well, there are 2.2 pounds in every kilogram. So I could give you something in pounds and ask you to convert it into grams or kilograms. So all these things I'd like for you to consider, and then once you feel ready, go ahead and start the homework and just hammer it out, just rock it out, and you'll do wonderful. Have a great day.